In today's video, we have a question that says that an elementary gas phase reaction. So there is a keyword here, elementary gas phase reaction. 2A plus B going into C takes place in a CSTR at constant temperature and constant pressure. So constant temperature means our system is isothermal, and then a constant pressure means it's isobaric. The feed is equimolar in A and B. So our FA naught is equal to our FB naught because the feed is equimolar in A and B. Find the volume of the reactor needed to achieve a 90%. So our X here is 90%, it's our conversion. And the reactants enter at 25 dm³ per second. So that's the volumetric flow rate. 25 dm³ per second. Take K to be 10 dm to the power 6 per mole squared second. Now, because you want to find the volume of the reactor, and then the reactor is a CSTR. So for the design equation of a CSTR, V, which is the volume, is equal to FA naught X all over R, where R here is the rate equation in terms of the reactant. That's why there's a negative V. So now with this, we need our FA naught, we need our X, and we need our R. So with the rate equation, our R is equal to, so we are going to write the rate equation based on the reaction. We have two reactants, so K concentration of the reactant raised to their exponents, which is their orders. Now because the reaction is an elementary gas phase reaction, so the elementary here means that the order of the reaction with respect to each of the reactants will be equal to their stoichiometric amount. So for A, the order with respect to A is 2 because its stoichiometric amount is 2, and the order with respect to B is 1. So A squared and then B to the power 1. So this becomes our rate equation. R being equal to KCA squared CB. Now with the conversion here, because we have two reactants, we have to determine which one is the limiting reactant. So the limiting reactant now becomes the conversion for the overall reaction. So how do we determine whether a reactant is the limiting or the excess? So in our previous video, I said that to determine whether a reactant is in limiting or in excess, we have to know the inflow of the reactant. So for A, it's FA naught, and for B, it's FB naught, but then they are the same, so we can just write FA naught for B also, and this for A. And then we have to divide their stoichiometric amounts by their inlet flow. So for A, it is 2, so we divide here by 2, and for B, it's 1, so we divide here by 1. So then we get FA naught over 2, and then for B, we get FA naught over 1. So after evaluating this, the smallest one becomes our limiting reactant. So if FA naught was, let's say, 10, when we divide by 2, we get 5 here. And then if it is 10, we divide by 1, we get 10 here. Since 5 is less than 10, our limiting reagent is A. So reactant A is our limiting reagent. Therefore, the conversion of A becomes the overall conversion of the reaction, which is 90%. So after getting that, then we have to make good use of the stoichiometric table. Our CA can be written in the form of CA naught 1 minus X. Now for our CB, because A is the limiting reactant, you have to write CB in terms of CA naught or in terms of the conversion of A. So that becomes CA naught multiplying theta B minus B over AX. We did this from the stoichiometric tables we did. So 2A plus B going into C. We say that we first have to divide 2 by the coefficient of the limiting reactant. And that gives us A plus B over 2 going to C over 2. So this part is what we call the B over A. Because if it was in this format, then I'm going to divide 2 by A, and then our B over A becomes this. Now our B over A here is equal to 1 over 2, this. And for our theta B, we derive that theta B is equal to FA naught all over FB. No, so it was FB naught FB naught all over FA naught. That's what we had as our theta B. So now we have our theta B, we can just substitute it here. And from the question, FB naught is equal to FA naught. And so when we divide, our theta B becomes 1. And our B on A is also half. So substituting everything here, we are going to get CB is equal to CA naught 1 minus half X. And then we are going to get, so this is what we are having for our CB. And then our CA is equal to CA naught 1 minus X. Yeah. So the next thing is, how do you find our CA naught? Because that wasn't given in the question. So to find our CA naught, we need to find our total concentration. Right? So the total inlet concentration, and because it's a gas, we can see that PV is equal to nRT. And then we can divide 2 by volume. And then we get N over V, which is concentration. So we can get P is equal to C total RT. So when we want the initial concentrations, let's have to put in our initial values. And our CT naught, which is our total initial concentration, will be P naught over RT naught. And this can help us find our total initial concentration. Our P naught was given as 16.4 atm. So 16.4 atm divided by, because our pressure is in atm, our R here is supposed to be 0.082 atm decimeter cube. And then our temperature here, so per Kelvin. And our temperature here is 500 Kelvin. So times 500 Kelvin. We could either convert the pressure into Pascal so that our R here becomes 8.314 joules per mole Kelvin. Or we could leave the pressure in terms of the atm, and then our R here becomes 0.082 atm dm cube per Kelvin. So when we evaluate this, we get our total inlet concentration to be 16.4 divided by 0.082 times 500. So we get 0.4. So atm divides atm, Kelvin divides Kelvin. So we get, there should be a mole here. So 0.4 mole per dm cube, because even R is 8.314 joule per mole Kelvin. So you should get that. And joules is pressure times volume. So in terms of atm, we have atm and dm, so the mole should be there. And then we get our initial total concentration to be 0.4 mole per dm cube. Now we need CA naught, the initial concentration of A, not the total. So to get CA naught will be the mole fraction times the total initial concentration. And the mole fraction of A will be the flow rate entering of A divided by the total flow rate. That will be FA naught plus FB naught. But then FA naught and FB naught are the same. So we get FA naught over 2 FA naught. And then we get 0.5. So our mole fraction inlet of A is 0.5. Then we can get our concentration. CA naught is equal to 0.5 times 0.4. And that will give us 0.2 mole per dm cube. So our initial concentration of A is 0.2 mole per decimeter cube. So this. So now we have our initial concentration. The next thing to do is that we have to substitute everything into the rate equation. We say the rate equation is KCA squared CB. Now we know CA. CA is this. So you have to substitute KCA naught 1 minus x everything squared times CB. So CB is CA naught. So this is what you have for CB. CA naught 1 minus half x. So when you evaluate, I going to get R is equal to K. So CA naught squared multiplying 1 minus x squared. Everything multiplying CA naught 1 minus half x. So CA naught. We get R to be equal to KCA naught cubed 1 minus x squared multiplying 1 minus half x. Our x is 90%, which is 0.9. Our CA naught, we had it to be 0.2, and our K is 10. So you can just substitute everything here. We have R being equal to KCA naught cube 1 minus x squared multiplying 1 minus half x. When we substitute 10 multiplying 0.2 cube multiplying 1 minus 0.9 squared multiplying 1 minus 0.5 times 0.9. So doing this, we are going to get our rate to be 10 times 0.2 exponent 3 times 1 minus 0.9 squared multiplied by 1 minus 0.5 times 0.9. We get our rate to be 4.4 times 10 to the power negative 4 mole per dm cube second. So this becomes our rate 4.4 times 10 to the power negative 4 mole per dm cube second. Now our volume is equal to FA naught x all over R, which is our rate. We need our FA naught. So our FA naught is equal to concentration, initial concentration times our initial volumetric flow rate. So we are given our initial volumetric flow rate to be 25 dm cube per second. Because you are dealing with gases, if you had wanted to find Fe, then Fe would have been Ca times V, not V naught. So to find our V would have used 1 plus epsilon x V naught T naught over T times P over P naught. And because it's isothermal and isobaric, this part goes to 1. And we are left with 1 plus epsilon x V naught. So this is what we would have used if we wanted to find Fa, because we would have needed V, and then because it's gas phase reaction, V would have been this. But now because we need V naught, and then V naught was given the question already. So Fa naught now becomes Ca naught 0.2 times 25. And then we can get our Fa naught to be 5 mole per second. So you have to substitute that here. So our volume now becomes 5 times our conversion is 0.9 divided by our rate, which is 4.4 times 10 to the power negative 4. So this gives us 5 times 0.9 divided by 4.4 times 10 to the power minus 4. And then we get 10227.27 decimeter cube. So our volume becomes 10,227.27 decimeter cube. So if you wanted to convert this into meter cube, that would be 1 meter cube is equal to 1000 decimeter cube. You're going to move 1, 2, 3, and that will give us 10.227 meter cube. So this becomes the volume of the reactor.